Welcome back to Unit 3, Section 6.3. The goals of this lesson are as follows. Again, you'll be able to perform addition, subtraction, division, and multiplication operations given two functions and state the resulting domain. And you'll also be able to evaluate compositions of functions. Please write these down at the top of your notes and have them ready, along with the additional notes we're about to do for tomorrow. Okay, this is directly from your textbook. So in section 6.3, you can find this in your textbook and copy it on your own. It's just the basic operations we're going to be doing: addition, subtraction, multiplication, and division. Adding two functions or subtracting two functions is just combining like terms. We've done this already. We have some examples here: f of x plus g of x. Given f of x is 5x and g of x is x plus 2, we're talking about these functions up here. That's what they're using these examples below. When we add them, h of x is f of x plus g of x. It's adding the two functions. They combine like terms. We get 6x plus 2. Subtracting it, we subtract them, we get 4x minus 2. And that's because, remember, you're distributing that negative sign to both terms. Multiplication and division. Once again, you're just multiplying them together. You're using distributive property or FOIL or the table method to multiply, but that's how we got 5x squared plus 10x. And then dividing them, you're just stacking them on top of each other and then reducing if need be. The key thing, because we're going to talk about domains, remember domains are the inputs of a function. So whatever you're putting into a function, that is the domain. Sometimes you're limited on the domains. For instance, in this last example here, h of x equals 5x plus 2 over x plus 2. The domain is all reals except x equals negative 2 because we can't divide by 0. So sometimes domains are limited. For the rest of these examples, the first three, its domain is all real numbers because it doesn't matter what we plug in to f of x or g of x. You get a real number output. There's no ratio, so there's nothing we can't plug in. Okay? And it talks about it here that the domain of the quotient does not include x values for which g of x equals 0. Power functions, there's a different new family of functions. We've done a few of them already, but you can see the definition of a power function is y equals a times b to the x. Here. A times b to the x, where a is a real number and b is a rational number. Okay, so rational numbers can be integers, okay, but they can be fractions as well for this. So please, if you need to, pause this and finish copying it down before you move on. Okay, let's do some examples of adding and subtracting some functions and then stating the domains of the result. F of x plus g of x. So here's f of x, here's g of x. Let's add those together. Negative 2 times x to the 2/3 plus 7x to the 2/3 power. They both have x. They both have the same exponent, so we can add the coefficients. We get 5x to the 2/3 power. And let's look at number 2. Now let's subtract them. It's the same two functions. We're going to subtract the coefficients this time. Same thing. Negative 2 minus 7 is negative 9x to the 2/3. So it's very similar to what we've done in previous sections. Let's answer question number 3, the domain. Okay, so the domain of the first problem, f of x plus g of x. Well, the domain when we put for f of x is all real numbers. It doesn't matter what we plug in. Okay, it's all reals. It's not reals, it's all reals. And it's the same for g of x. We can plug in any real number we want. So if it's all reals plugged in and we don't have any fractions on when we're done, then the domain of this is still all real numbers. Over here, same idea. It was all reals going in for both functions. I don't have any fractions, so I don't have to worry about making the denominator 0. So it's all real numbers for f of x, or f minus g as well. The only time it's not going to be real numbers is going to be when you plug some number into a part of the function and it makes an undefined value. Let's practice multiplying and dividing. The other two operations we are accustomed with. So here's our f of x, here's our g of x this time. So f of x is 3x times x to the 1/5. Remember, when you multiply, we multiply the coefficients. 3 times 1 is 1. And with the variables, we add the exponents. That's really to the 1 power. So 1 plus 1/5, or 3x to the 6/5 power. And then over here for number 5, very similar, except we're going to divide now. 3x over x to the 1/5. So 3x, we can simplify this, right? We subtract the exponents, the bases are the same. 3 divided by 1 is 3. X to the 5/5 minus 1/5, because really it's x to the first power here, which is 5/5, or 3 times x to the 4/5. Now our domains. Before, it was all reals for both f of x and g of x, and multiplied, and we didn't have any fractions. So the domain is all real numbers. Now, this is where it's going to be different here for number 5. G of x is in the bottom. I can't let g of x be 0 because it's dividing f of x. So what would make the bottom function 0? Well, plugging in 0 would make the denominator 0, which we can't have. So for this domain, we would say all real numbers except or not equal to x equal 0. It's going to be different for every function. Whatever makes the denominator 0 when you're dividing them cannot be in the domain. Here's something completely new. You probably have not seen this before unless you've taken Algebra 2 previously, or I doubt very seriously you got to it in Algebra 1, but you do never know. The composition of two functions. It looks like nested parentheses. It's h of x equals g parenthesis f parenthesis x parenthesis. Okay, and you can also see it written like this. G following on 0 f. G following up, that little 0 means following up. So that's an alternative way to write it. But basically what it's saying is you work inside out, or right to left in this case, if you use a g following f. For f of x, you evaluate a value in the function f in this case first, then you plug that value into g. Okay, here's kind of a visual representation of what that really means. Okay, the domain of h is all the set of h values such that x is the domain of f, and f of x is in the domain of g. Okay, so it's kind of a visual way to look at the domain, the ranges, and domains, and how that all works out. Let's try some example. So we're going to simply evaluate these functions. G of f of 5. What you do for this, for number 8, G of f of 5, we start by plugging 5 into f of x. So we're going to plug 5 into f of x. f of x is 3x minus 8. So 3 times 5 minus 8, 15. 3 times 5 is 15, minus 8 is 7. So now we're going to evaluate 7 into g. 7 into g, that's 2x squared. So 2 times 7 squared, which is 49 times 2, or 98. So we work inside out. The number goes in the inside function first, get a value, you plug that value into the outside function, and you get your result. Number 9, f of g of 5. Well, g is inside first now, so we're going to plug 5 into 2x squared first. So 2 times 5 squared is 25 times 2, which is 50. So we're going to plug the 50 into F. F is 3x minus 8. So 3 times 50 minus 8. 150 minus 8 is 142. And this looks kind of weird, but f of 5, can we do that? Yes, we can. We can do a composition of a function within itself. F of 5, well, we're going to start with the f function. So we're going to plug 5 into f. 3 times 5 minus 8 is 15 minus 8. We've done this before, 7. So we're going to plug 7 into f again. The result, 3 times 7 minus 8 is 21 minus 8, or 13. And finally, we'll do it with g one more time. G of 5 still? Yeah, 5. So we're using the same input all 3 times, but noticing we're getting dramatically different results depending upon what functions and what orders they are composed together. G of 2 times 5 squared. We've done this one before. It's 25 times 2, or 50. So now we're going to plug 50 back into G again, and we get 2 times 50 squared, which is going to be 2,500 times 2, or 5,000. So the whole way this goes, basically, hopefully you're seeing the pattern is you plug it in first. The output you get from the innermost function value becomes your input the second time for the second function. So an output becomes an input. It's like doing 2 things back to back. You have to get the inside value output first to find out what your next input's going to be. Okay? So you just work inside out. The innermost function first, the outermost function. Could we compose 3 functions, 4 functions? We could. We probably won't be doing much of that in here, but we can do that, and we may do that eventually one day down the road. So did we hit our targets? I think we did. We did all the basic operations, addition, subtraction, multiplication, division for 2 functions, and we talked about the domain that results from doing those operations, and we also learned how to compose 2 functions. Different compositions working inside, out. You keep the innermost function first, take that output value, it becomes your input for the next function. Make sure you have all this down, and we'll see you tomorrow in class.